Assalamu alaikum everyone.
Wa alaikum assalam, sir.
Madam, are you listening? Madam? Okay. We welcome to all of the participants from the Department of Mathematics, University of Education, Lahore, Multan campus. We are thankful to our Vice Chancellor and Campus Principal Professor Dr. Mohammad Asad Mir for giving opportunity to conduct online seminar or
Dr. Noor? Hello?
Dr. Sobia Sadiq, are you ready?
Yes, can you hear me?
Okay, why not, madam? I think we should start.
Okay. So firstly, thank you organizers for inviting me to this event, so intellectual event. So I think I should start my talk.
Yes, madam, you can share your slide.
Is the screen showing?
Yes, madam, you are sharing your screen. but I think please width थोड़ा सा इनको लार्ज कर देना, ज़्यादा बेहतर होगा.
Is it fine now?
Yes, yes, madam. Now it is fine.
Okay, should I start?
Yes, why not, madam?
Okay, thank you. So, Assalamu alaikum.
Walaikum assalam.
When I was invited for this seminar, there was one thing that was in my mind, that I should speak on a topic which should be very easy for the students to understand and for the layman, for the people who do not know about the general theory of relativity. So I thought that I should kept this talk very basics, and so that's why I have added no research work and kept it very basic. So let's come to the talk. As you can see from the title, there is one significant thing on which I am going to emphasize is the general theory of relativity. In this talk, I will basically discuss the foundations of general theory of relativity, the description, and then the applications of this theory. So here is the layout. Firstly, I will discuss the special as well as general theory of relativity very briefly. Then we will move towards the description of our universe and the role of general relativity to discuss the universe. At the end, I will share some topics of interest and some recent lines of action. So, one of the most important entity of the nature is the gravity. Basically, there are four fundamental forces in nature. First one is the weak fundamental force, strong fundamental force, then electromagnetic force, and the fourth one is the gravitational force. From the very beginning, when we started to study physics, we had the concept of gravity as the force of attraction. That is, when there are two bodies, then one body is attracted by another body. And when you throw some object from the top of the building, then it moves towards the earth, which is called the terrestrial gravitation. You can observe that the heavier bodies fall faster than lighter bodies. This means that more mass leads to the more gravitational force. And here the value of gravitational acceleration is given here, which is g equals to 9.8 meter per second squares. The idea of gravity comes in Newton's mind when he was once seated under an apple tree. Suddenly, an apple hit his head. He observed about that, and this observation caused him to ponder that how apple always falls straight to the ground rather than sideways or upward, and inspired him to eventually develop his law of universal gravitation. Here, the mathematical form of this law is given over here, which is known as Newton's gravitational law. According to this law, every body in the universe is attracted to every other body. That if you take two masses, first one is m1 and second one is m2, then they are attracted to each other with a force that is directly proportional to product of their masses and inversely proportional to the square of the distance between them. Here you can see from this formula that it is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Newton basically considered that the space and time are the absolute quantities and they do not depend upon the motion of the observer and the matter that is contained within the space. He thought that it is the gravity that holds our solar system together, but he was not sure about the gravity, that how the gravity keeps stars in their orbits and the orbital motion continues. So in fact, for the celestial bodies or stellar objects, we can think that how can massive objects attract each other without mediation of anything, or how can attraction between them be so immediate? So then came the idea of Einstein. Einstein was basically the patent officer and he used to meet his old friends. Some of them were studying physics, some of them were doing engineering. So they used to share their intellectual thoughts, and from there Einstein's passion for physics was developed. In 1905, he came up with the special theory of relativity, in which he unified the space and time and treated them as a single entity. So this theory has two basic postulates. The first one is that the physical laws are same for all the observers. That is, they do not depend upon the motion of the observer and the frames which we are taking. And the second one is related to the speed of light, which says that the speed of light in vacuum remains constant. That is, it is independent of the relative motion of the observers. These postulates of general theory of relativity lead to the following consequences. First one is the time dilation. Einstein did an experiment and he found that the moving clocks are slower than the stationary clocks, and mathematically you can see that there is a factor whose presence indicates that there is the time there is a difference between times measured by the stationary observer and the time measured by the moving observers. This means that time dilates. Second one is the length contraction. Length contraction basically means that the length contracts along the direction of motion and there is no change that appears in the direction perpendicular to the direction of motion, and again you can see that there is a factor due to which the difference occurs between the lengths measured by the stationary observer and the moving observer. The third one is the twin paradox. Twin paradox says that if one of the twin brother goes in space and the other stays on earth, then because the time dilates, so when brother comes back from the space and he is still young, but the brother which stayed on earth ages and becomes older, and this happens due to the time dilation. Similar to the special theory of relativity, general theory of relativity also has some postulates. First one is the principle of general covariance, which states that the physical laws should be stated in tensor form. Why? As the physical laws are examined according to the coordinate systems, and the physical laws should be invariant. That is, they should remain same for all the coordinate systems, and the tensors are invariant under coordinate transformation. So the laws must be written in the tensorial form. Second one is the principle of equivalence. It states that the gravitational and acceleration causes the space-time curvature and they are same. And Einstein stated that the acceleration and the gravitational forces are indistinguishable. So if acceleration produces curvature, so does the gravity. And so in order to understand the general theory of relativity or to work in the area of general theory of relativity, we need to understand some definitions. So here are some very basic definitions that should be understood. First one is the frame of reference. As we know that the points in space or events in space-times are defined through the set of axes, which is called the frame of reference. So when the time is unified with space, then it becomes the event, as you can see here. And when we measure the point in space, then it is denoted by x, y, z. But when we unify the time with these points, then it becomes an event, and it is denoted by x, y, z, and t. So in general relativity, space and time are treated as a unified entity. So there is a concept of space-time rather than space. So the space coordinates are treated as the 3 dimensions and time as the 4 dimensions. So as a whole, general theory of relativity is a 4-dimensional theory. The geometry of space-time is described as given in this equation, and it is given in the Cartesian coordinates, and it is known as the Minkowskian metric or Minkowski space-time. This metric can be written in different coordinate systems. So here is one example. If we write the metric in spherical polar coordinates, then it has this form. So Einstein basically identified the property of the space-time which is responsible for the curvature of space-time, and that feature of the space-time is the gravity. That is, the curvature is produced due to the gravity. As you can see from this picture, according to Einstein or the general theory of relativity, space-time is no longer flat, but it can be pushed and pulled or stretched and wrapped by the presence of matter, as you can see from this picture, because it is not flat and some heavier bodies are present in it, which produces the curvature in it. So gravity feels stronger where space-time is more curved and vanishes where it is flat. So for this space-time, because it is flat, so there is no gravity and no matter present. And here, because the curvature is present, so the gravity is heavier, and due to the presence of larger bodies or heavier bodies. A standard way to illustrate this is to place a bowling ball representing massive object on a stretched rubber sheet, which represents the space-time. If you place a piece of marble on that rubber sheet, then it will move towards massive object, or it may even be put into the orbit around bowling ball. So this happens not because a smaller object is attracted by the massive object, but due to its traveling on a surface which is deformed due to the presence of massive object on it, as it is very clear from this picture. In a similar way, gravity is no longer a force which propagates through the space-time, but the feature of space-time itself. And you can say that, what is the feature? It is the curvature. So John Wheeler summarized this idea by saying that matter tells space-time how to curve and space-time tells matter how to move. Human mind is always curious that how our universe came into being. Scientists believe that an explosion occurred and then in an instant the universe expanded with incomprehensible speed from its stable size origin to the astronomical scope. Scientists believe that at about 300,000 years after the Big Bang occurred, the universe consisted of molecular clouds. Gravitational forces caused clumping of this turning matter until at about 500 million years later, when large distinct quantities of matter gathered at the beginning of galaxies. Galaxies bound together into groups. Our Milky Way is a member of the so-called local group of galaxies, which also includes two other relatively larger galaxies, Andromeda and Triangulum, and 30 or so dwarf galaxies. On a larger scale of clumping, groups of galaxies bound together to form superclusters. Our local group of galaxies is a part of Virgo superclusters. From about 1 billion years after, gravitational forces pulled matter within the galaxies together to form stars. And basically stars are the luminous balls of gases that are held together by their own gravity. There are some questions about the stars that came in our mind, that how from where the stars are born, what are their ages, and how the stars die, what happens when they die. So we can find the answer of these questions by using the relativistic astrophysics, which is basically the study of astrophysical phenomena within the framework of general theory of relativity. So general theory of relativity helps us to understand such phenomena. This picture basically shows the evolution of the star. Here you can see that initially, if we have stars, there are three ranges for stars. First is between the 0 to 8 times solar mass. Second one is 8 to 25 times solar mass, and third one is 25 to 100 times solar mass. So for this range, if we have initial stars, and then some reactions occur in the stars, and it goes through different phases. As you can see from here, that first one is the red giant, then it becomes nebula, and the final state is a white dwarf again, in which the nova and supernova can occur. For the second range, the initial star, by passing through different phases, the last stage is the neutron stars, and for this range, the final state is the black hole. So this picture as a whole shows the evolution of stars, that we can say that the different reactions occur within the stars, and we can have different types of final states for the stars. having different masses. As you can see here, for the white dwarfs, the mass is less than 1.4 times of mass of the sun, and for the neutron stars, it should be less than 2 times of solar mass, and for black holes, these are very heavier objects and they have mass more than 2 times mass of the sun. So as a whole, human mind has always been speculating about the universe, that how it came into being, how will it evolve in future, and what are its matter contents. So the answer to these questions is given by cosmology, which is basically the study of the universe. It explains the origin, evolution of the universe and all the physical processes that occur in our universe. So the concept of modern cosmology was laid down in 1915 when Einstein proposed his theory of general relativity. Einstein established geometric standpoint of gravity and introduced a new concept of cosmos in terms of dynamical systems subject to precise mathematical modeling and physical measurements. So Einstein's general theory of relativity, as I told you earlier, that it basically relates gravity and curvature. So it basically relates the space-time geometry with the matter that is present within the space-time, and these equations are known as the Einstein field equations. And here the left side shows that it represents the geometric part, while this is the matter part. And here there are different terms such as here R mu nu, it is the Ricci tensor which defines the curvature within the space-time. Here G mu nu is the metric tensor, R is the scalar quantity, kappa is the coupling constant, and this C mu nu basically represents the energy momentum tensor, and it describes the distribution of matter within the space-time. So this energy momentum tensor can be expressed in the matrix form as given over here. So it has, you can see that it has 16 components. And this tensor has different forms for the different types of fluids. So fluids basically is a subclass of 4 states of matter, namely solid, liquids, gas, and plasma. It is defined as a substance that easily deforms when subjected to a shear stress. So generally there are 2 types of fluids. First ones are the perfect fluids. Perfect fluid are defined as a fluid that is defined by only its density and isotropic pressure and is known as perfect fluid. Such type of fluid is free from viscosity, shear stresses, and heat conduction. So the energy momentum tensor for such type of fluid is given over here. And here you can see that this is rho. It represents the energy density. This is pressure of the fluid. U alpha represents the velocity of the fluid. And this G alpha beta is the metric tensor. So here U alpha, I told you that it denotes the flow velocity. When we take pressure in this isotropic fluid, perfect fluid, we take when pressure 0, then it becomes the dust fluid. And dust fluid is a special case of perfect fluid for which the pressure vanishes and has the energy momentum tensor of this form as given over here. Then there are imperfect fluids. These are the fluids that constitute viscosity and capacity to conduct heat, and they can either be isotropic or anisotropic. Isotropic fluids are expressed in over here. It is the energy momentum tensor of the isotropic fluid, and here are different terms which expresses shear tensor, bulk viscosity, specific density, coefficient of viscosity, heat flux, and the expansion scalar. And the second one are the anisotropic fluids. These are the fluids for which the pressures are different in different directions, and the energy momentum tensor for these types of fluids is represented over here, where in this equation the P tangential and PR represents the tangential and radial pressure respectively, whereas S alpha indicates the space-like vector that is orthogonal to the flow velocity. So to study the universe, Einstein basically made first attempt and constructed a realistic cosmological models in the framework of general theory of relativity. Einstein believed that our universe is static, that is, it has no beginning and end, so he added this term, g mu u lambda, to the Einstein field equations, and this lambda is known as basically the cosmological constant. He added this term because to introduce the repulsive effects so that it can counterbalance the gravity and the universe should remain static. So later some observations revealed that our universe is not static but it is expanding. So he thought that it is the biggest blunder of his life to add the cosmological constant in his field equations. Some recent observations by Perlmutter, Smith, and Rees confirm that our universe is expanding, and it is expanding in an accelerated way. And they won the Nobel Prize for this observation. But why our universe is expanding? So this late-time accelerated cosmic expansion is a major issue in cosmology. In fact, there is a force that is pushing universe apart, and it is named as the dark energy. So in our universe, most of the energy seems to reside in empty spaces. This energy is gravitationally repulsive and appears to be the cause of speeding up the observed expansion of the universe. The recognition that dark energy appears to exist has completely altered the landscape of theoretical physics and driving astrophysics to launch new cosmic probes to detect its nature. If you want to understand that how our universe is expanding, you can simply understand it by an experiment. If you take a balloon and make marks with a marker on that balloon, when you blow that balloon, you can see that those marks that were made by a marker change their position. And if similarly, if those points that were marked represent the galaxies in our universe, then as the universe expands, then the distance between those galaxies increases, and so we can say that our universe is expanding, and it is expanding in an accelerated way. This figure shows that what the universe is made of, and here are the contents of the universe. So the 4% of our universe is represents the normal matter, while 21% is the dark matter, and the other 74% is the dark energy. And this blue portion is basically responsible for the accelerated expansion of our universe. So that was all about the general theory of relativity, and I told you earlier that we can use the framework of general theory of relativity to work or to understand the astrophysical phenomena as well as the cosmological models, or to study the phenomena that happens in our universe. Here is the list of topics of interest and some recent line of actions. So we can discuss some cosmic issues using different dark energy models, and then discuss the wormhole geometries, and we can also evaluate interior geometry of compact stars, and similarly the thermodynamical analysis of the cosmos can be done by using the general theory of relativity. Here is the list of references. So thank you.
Thank you very much. It was a nice talk with you. We are great for start. Thank you very much. It would be better to send your PPT to me.
Sorry, Dr. Noot, I can't hear you.
I think I have net problems, madam. Are you listening me?
Yes.
Now are you listening me?
Yes, Dr. Noor.
Okay, madam. Thank you very much for your nice presentations. It was full of knowledge, and inshallah, in future, we would like to invite you again for the next or another seminar. It will be better to email me your lecture, PPT, for our future use. Students, any question if you have about the seminar?
Sir,
Yes,
I want to say that
Bilal?
अस्सलाम वालेकुम मैम।
Walaikum Salam.
मैम ये आपने हमें ये बताया कि ये जो स्पीड ऑफ लाइट है वैक्यूम में ये 3 मल्टीप्लाई बाय 10⁸ है। मैम सिर्फ ये वैक्यूम में ही रहेगी या हर जगह ये सेम ही रहेगी स्पीड ऑफ लाइट?
वैक्यूम में सेम रहेगी।
ओके मैम, थैंक्स।
Yes.
Bilal? Bilal?
yes, ma'am. Ma'am, I want to ask that is cosmology is any specific branch of physics, or it is a mix-up?
Physics is basically the study of physical phenomena that happens in our daily life, or you can say that in our universe. But as a whole, cosmology is basically the study of the universe. So it is not the branch of physics.
Okay, ma'am. And it was nice presentation, and it helped me a lot, ma'am. Thank you.
Thank you. Thank you.
Any other question? Participants? Madam, I think there is no question. Once
Yes.
again, thank you very much. Thank you.
Thank you so much. Thank you.
I think we should get the call. Thank you all. Thank you all of the participants. Thank you.
थैंक यू सर।
Thank you.